Third and final speaker is Navid Asadi, and he's going to talk on physical assurance and inspection of electronics. Navid is an assistant professor in the Department of Electrical and Computer Engineering at the University of Florida, and his research is mainly focused on the physical inspection of electronics from device system level. He investigates novel techniques for integrated circuit counterfeit detection and prevention, for chip-level reverse engineering and anti-reverse engineering, invasive and semi-invasive physical attacks. And in his career, he's received several Best Paper awards for presentations on these topics. He's also a co-founder of the IEEE Physical Assurance and Inspection of Electronics Conference. Navid.
Thank you, Ivor. Appreciate it. Thanks for the introduction. Hello, everyone. I guess I want to thank the organizers of this great series of the talks. Yesterday, a good number of talks on different topics, supply chain security. Today, Matt and Ajay, great talks, and made my job easier to probably skip through some of the original introductions for this topic and get time to get into some details. So this talk is gonna be probably 5,000 level, if maths was 10,000. So we're gonna go down to 5,000, a bit more details of the physical assurance, but just touching on the different methods. This is an area that is getting interest. This is an area which where the failure analysis is meeting the security and haven't been explored and got enough attention that it needs from my perspective. There is a lot of new modalities, a lot of the cross of the advanced computation and the different physical modalities is bringing in new items onto the table. And they can be used for the assurance. Of course, it is a difficult process. There has been good progress already on some of these modalities, but it is going to be in a dynamic status. As the new packaging, new chips, new designs are coming out, these methods are going to also improve because fabricators and foundries need them for the yield analysis. But what the assurance is basically use them and apply them on a higher scale volume and try to achieve 100% assurance. Okay, so I guess everyone is fully aware of this model of fabrication and complexity of the supply chain. I'm not going to bore you with the details of it. Obviously, the design, fabrication, packaging, distribution are all around. We have third parties. We have those small vendors that can be potentially a vulnerability in this process, and insiders, and a lot of different topics that were discussed already over the past two talks as well as yesterday. What I want to probably point out of these process is the counterfeits. So yesterday, Michael was talking about the counterfeits, very good and interesting talk. There has been a number of different counterfeits. Right? We talk about the recycled, we know remarks. Past 5 to 10 years, recycled chips, we're getting a lot of attention. If you have a chip which is aged, if there is a chip which is remarked, there is discoloration, probably some other type of defects on the package that you can get from an optical image or any other surface imaging, could be a sign of a counterfeit. Again, not necessarily a counterfeit, but could be a sign of counterfeit. Thankfully, the past few years, by raising the awareness for such recycled chips, which I still believe that they haven't checked the recent report, but I still believe that they are actually the market for counterfeits still includes a lot of recycled chips. But the two ones which are very interesting and we need to actually pay more attention are the cloned and the tamper chips. So basically with the clone versions, without spending a penny on the research and development. Same chips can be built for monetary benefits and advantages by an adversary, and they can go into the market. And the other case is the tampered and Trojans, which we have heard already a bit about this. We have heard about the big hack. We discussed this. A couple of speakers already also talked about it as well. And there are other stories as well. I'm sure many are familiar with it, but other than big hack back in 2018, there was a story with the NSA a few years before that. There was another story about the tampering on a board in Brazil back in 2017, where they could tamper with the reported volume of the fuel in gas stations and basically escape from paying the right amount of the tax to the government. Again, 2020, another case, a router that Monta Alkins was working on it, adding another chip on the board. It was a router and could bypass a lot of different security primitives. So this has been going on. This is on the tampering part. But on the other side, if we look from an attacker perspective, there are a lot of assets that can be extracted from the chips. Right? We do all the design, about 60–70%. The recent report came out. We have about 60–70% of the design done in-house, and then fabrication and packaging is all out. So we have a lot of assets on these chips. If we look into different blocks here on the processors, the software, the firmware, we have on the crypto accelerators, the key, HMAC, on the memories, again, we have also different type of keys and protected data that we have to make sure they stay protected. But on the other side, there are these physical-based methods as well, which can be used for extracting these data. Yesterday, Nader talked about the side channel, but when we look at it, which requires its own process, sometimes for different chips may be complex, but if someone has access to these advanced failure analysis techniques, extracting the data is not going to be very difficult. And for us to close our eyes on these advanced technologies is just wrong. We have to be aware of the vulnerabilities. We have to know how such an attack can be done to be able to come with the solutions. And this is not beginning. There has been a lot of work. Electronic inspection and physical inspection is out there many years. Automation, EDA tools, Saverio talked about them. There are different types of these tools. And we want to try to automate as much as possible. Billions of transistors on a chip, thousands of components on the PCB, assuring them in an automated way and taking human out of the loop is a difficult process, but there is a lot of good foundational work. For the physical inspection, I like the couple of slides that AJ had about the optical and also the X-ray imaging for the inspection. Thankfully, we do see more and more involvement of companies with such methods. Physical inspection used to be very manual, having a lot of subject matter experts. And as soon as human comes into the loop, it's going to be to some degrees on the edge cases, depending on the decisions that human takes. So there are a good number of efforts trying to quantify the assurance. Quantifiable assurance has been a topic, and we have been working on it. But if we look into this big picture, a lot of different industries are going into the imaging-based or characterization-based assurance. Imaging techniques are getting better. The computational power is getting better. 10, 15 years ago, we didn't have these smart and intelligent inspection methods as we have now. Medical, I think they have been actually on the forefront of this. And there's no surprise, obviously, in that aspect. There are probably more and more investment. And I'm probably going to echo again what Matt said, invest. If this is critical, we are nowhere close to where, for example, medical is doing in imaging. Other areas, material engineering, mechanical engineering, imaging, and characterization is evolving, is changing. We have new methods right now with the TPUs and different neural networks application, and the availability of the data as we get them, they're improving. And electronics are not going to be different. ICs and PCBs, they're not going to be different. We can use these techniques for such analysis, going down to few microns, going down to few nanometers, trying to look into the whole physical structure, or come up with fingerprints which are not dependent on something that is enforced to be put on a chip. Fingerprints that are purely based on the material, the structure, the integrity of the chip, and so on and so forth. Okay. These tools may be familiar to many of you or some of you, and we have been lucky to actually have all of them in our lab. About 10 million plus equipment in University of Florida, from focused ion beams to scanning electron microscopes, optical imaging, helium ion imaging, probing, optical emission and laser emission stimulation, terahertz spectroscopy and imaging, which I don't have the image here. This should be probably updated, and a lot more on the sample prep side, obviously. And these are basically the tools that we need to educate our next generation workforce on it. So if I remember, and I put a post about a couple of weeks ago on my LinkedIn about some of these equipments when we installed them back in 2017, and this was the first one in the state of Florida, and I remember talking to the installation to the engineer who were doing the installation, and I was told that by that year, there were about 6-7 of that equipment installed in the whole US, and out of US, it was like 60 or 70. So we are behind in investing in this area. And if we want to stay ahead in the semiconductor and electronics, then we have to learn from the material produced by these equipments. So the rest of the talk, I'm gonna go into that 5,000 level now. So looking into different methods for the physical inspection and assurance. I'm gonna divide it into ICs and PCBs, two main components in the electronics, and destructive and non-destructive. Obviously, non-destructive is much more appealing, specifically for government, even commercial as well, with the bulk of components, thousands of them have to be assured every week, or sometimes daily. Non-destructive is a much better approach. Let's look into some of these methods, the ones that we have worked on, developed some of these, where we are and what are the requirements to get to a level to have that 100% assurance. So ICs and destructive approach, we had the discussion on reverse engineering of ICs a bit yesterday. So this is an area that a handful of companies are actually worldwide involved in this. The ones that we know, again, there are probably going to be more that we don't know when they come out, and then there is a news, we will know about them. But if there is anything out of it, then there may be even ahead of us. But the reverse engineering in general is a very complex process, from getting the chip, the packaging, the encapsulant and that polymer material, getting into the die and removing the material one at a time, trying to collect the images. And by the time, and there's a lot of challenge there, but by the time you collect all these images, the next step is going to be where computer vision, machine learning, and deep learning comes into the picture. And we do have the need to get the help from these scientists in the computer vision community, trying to extract and segment the different components and eventually extract the functionality. So the better your images, the less challenge we have with the computer vision. So the efforts right now are on both ways, trying to make the image better and better, and also improving these computer vision analysis more advanced and more. So the delayering process, back in a couple of years ago, we have been working on it with the plasma FIBs that can open up a large area on ICs, about 1 by 1 millimeter. We developed a recipe, a process that with the FIB, one can automatically delayer a chip and collect the images. So basically you run this algorithm on your FIB machine, and next day or in a couple of days, you come in, you have a stack of images from about the 1 by 1 millimeter area, maybe 14, 15, or 20 different layers, and which will include about 40 or 50 different slices. Okay, so every slice that the material is removed may include a portion of a layer. Every layer is probably involved of 2 or 3 slices. So we have to go, we have to remove the material slowly so that we make sure that we capture those nanometer or sometimes even smaller than nanometer features. Okay. And once we have it, then these stack of images can be created. So here there are 2 short videos. At the bottom right are the raw images of this images from a credit card. So this was actually a credit card that we sacrificed, and you see the one on the die, basically the whole die from the backside, the silicon can be removed. Then the rest, these windows can be opened up with the plasma FIB and start collecting the images with some very preliminary image analysis. We can get rid of the noise and then try to connect the different features and make sense of the design. But that is slow. They're right now collecting images in the nanometer scale level, delayer them, go to the next one, and then do the imaging again. There was a program by IARPA called Raven 4 or 5 years ago, and millions of dollars of funding for the program to be able to actually make it faster and faster. So new SEMs were developed to collect images, and instead of using 1 beam, actually using even more, 60 or 90 beams or a distribution of the beam to collect the images. But on the image analysis side, there is also a lot that can be done. What you would see here are 2 images of the exact same area and exact same preparation process. So there is no further removal. Up left, there is a low KV imaging under SEM, and then bottom right, there's a high KV image under the SEM. So what you see on the first one, the low KV are just the traces of the middle layer 1, but the high KV shows the middle layer 1, the contacts that are connecting the middle 1 to the middle 2, and also on the subsurface feature, we do see middle 2. So this is a complex convolved image. There are techniques that they can be extracted, like PSF, the convolution functions, and machine learning AI can help with this as well. And it's a work in process. We are working on it. So this will help to reduce the delayering process at least by a factor of 2 or 3. All right. And in addition, there are other imaging techniques as well. We do improve these imaging methods. Again, what you see here is the comparison of SEM images with helium ion imaging. Again, same area, same chip. The SEM image, low KV, shows the doping region of an IC, which is prepared and opened up from the backside. A high KV shows a lot more features of it. But we know on all these chips, we do have also some dummy features, right? There are a lot of them because of the mechanical stability and so on and so forth, which cannot be a Trojan if they are not connected to the circuit. If they are just there to the mechanical stability and they are just not in the circuit, they are not going to be a Trojan. We talked about the dormant Trojan yesterday, I guess, as well. And to use SEM images and do the analysis with an SEM, we still have to extract everything, right? But the features and the capability of other modalities, like this one, which is a helium, you do see all those dummy features, which are for mechanical stability, they actually don't show up because of the high passive voltage contrast for the helium imaging. So if one was supposed to use any of these dummy cells and make them a Trojan, then they will start to show up because they will get connected. So it's based on the voltage contrast, very basic principle technique on failure analysis, but hugely reduces the complexity of image analysis and higher resolution, as you see, which eventually makes the process of computer vision as well easier. Okay, so bottom line, these processes are getting better, but we have to have data. We don't have enough data to improve those AI-based techniques. Data from different ICs, data from different SEM machines, different images with different noise, distortion, so that we train the algorithms. And unfortunately, as soon as we talk about the data, then the concept of the proprietary comes into the picture. But I want to highlight it again here that what the algorithms need to learn are the noise and the type of the features that are used, not the whole design. So even if there are ICs that images are collected randomly from different places with different SEM images to just cover enough of the cell types and their patterns, eventually the need for training these algorithms is to have them understand the noise. And that would help with extracting the real features there. So we have started to create our own database. We looked a lot online, try to see what is there that we can use it, but eventually we started to have our own database. Right now, about tens of thousands of images from 28 and 14 nanometer on the database, and hoping to have more and more from different vendors, different SEM machines, which will hopefully help the this area for assurance and community as well. So on the ICs, we have also probing, a big topic. I'm just gonna touch upon this topic. A few years ago, the discussions on micro probing, we still have these micro probing machines here and there. Then nano probing tools came in, and after that, pico probing. So, and this size is referring to the tip of the size of the tip of these probes. So now we have these probes as small as a few picometers. So and with the fibs and some microsurgery on the chips, if an adversary has some information, they are able to bypass some security perimeters and extract some information. But on the other side, if we are working on the techniques and methods that by understanding the dimension and by understanding all the features of the microsurgery with the fib, how we have to design these chips, put their middle layers in a way that one would most probably cause a problem or raise a flag during this process of the microsurgery. All right, so work on progress. Again, as we are getting into new chips, they are getting more and more difficult, but it's still something that is possible. Okay, so I'll have probably a few cover the next 3-4 slides, then we can look into a pause for a few seconds if there are any questions before I jump into the PCB. The non-destructive approaches are on the other side for ICs getting a lot of attention over the past year or two. 2020 December, we presented a paper key left under the mat on how the data on motion on an IC may be extracted by different failure analysis machines. So optical inspection and optical probing is the basic physical principle behind it. We have 3 major modalities under optical inspection. Photon emission, which is a passive technique. Basically, what is doing is collecting the emission from the activity of the transistors and integrate them and create a 2D image. Okay, so if this 2D image and the frequency of collecting these images is high enough, you will be able to connect that and relate that to the functionality of the chip. Laser stimulation is the second mode where one can inject electron holes in some transistors and potentially change its status from 0 to 1 or 1 to 0. Photoelectric laser stimulation or thermal laser stimulation are the two main topics. I'm not going to go into the details of them, just touching up on these topics. If there's more interest, I'll refer you guys to the host paper that we had in 2020. And finally, the EOP and EOFM, the electro-optical frequency mapping and probing, which is recollecting or collecting the reflected laser that is shined to the transistors. And if the transistor is having an activity on a specific frequency, the modulated laser will also have that frequency. And looking into the frequency and the phase, one can just optically probe or in some way or in another way, just do contactless probing. So a handful of companies are providing these machines, used to provide these machines. Again, failure analysis tools, Matso, Semicaps, and a couple more. But we are actually seeing more and more of these companies that, small companies here and there, they can put together sources and detectors on a vibration isolated table and target a specific point in an IC and try to extract vulnerabilities. We are lucky to have one of these in our lab and have done our studies. What we did and presented in that paper I mentioned was understanding the data at motion as they come out of the they come out of the memories. All right, so they pass through the registers. For a logic locking example, we have keys on the chip, and these keys have to eventually come out of the tamper-proof memories and be sent to the logic. And by the time they come out, they pass through the registers. One can extract them. So basically, a brief overview of it is by connecting a chip and looking into the emissions and the EOFM and EOP signals and sending different commands and comparing them when you are sending zeros or all ones, but you know your key is going to be same, okay, you will be able to extract that. All right, so it's a lot to cover in few minutes, but very interesting work that we did with my student Tanjid, and was published in the Host 2020. So I'm going to probably pause for a few seconds. I don't know, Ivor, if there are any questions before moving into the printed circuit boards.
Well, thank you, Navid. This is fascinating stuff, and I'm alarmed to see that you can go in and unlock the keys. What is the application for that technique?
So the logic locking is a technique used. I'm sure everyone is probably familiar with logic locking, but it's a technique used to basically implement or insert your key as a trusted foundry after you get your chip through the fabrication. So you hold the key and you put it in, you run your functionality when the chip is fabricated and is back on the on-site, on a trusted site. And by putting in that key, you will be able to run the logic, right? So if you don't have that key, then you won't be able to run the logic. But that chip goes back into the market after the chip is, after the key is inserted. So if someone has access to that chip, they will be able to extract the key. And that is an attack. We talked about the insiders. We talked about the different vulnerability points. But basically, using the optical, you will be able to extract that asset, which is a key. Does it answer the question? So the application of the logic locking is protection, trying to actually obfuscate your logic that you have designed from a manufacturer. So when it comes back to you by applying the key, you get the full functionality. But again, as soon as you put the key back in, if there is an access to that chip, one would be able to extract that key, which runs your whole functionality.
Good. Well, we have one question, which is almost the complement of my question. What are the state-of-the-art methods to camouflage or obfuscate and mitigate the reverse engineering methods that you have described? How successful are these countermeasures, and what is the outlook against these types of attack?
Very good question. I would say that is a work in progress. We are working on, and there are some works out there, material-based and circuit-based. So this is one of the favorite topics of mine, that we should talk about it, because we have to have the whole community to talk about it. If we want to do material-based solutions, then who's going to enforce the foundry to actually apply them into the CMOS fabrication process? If we want to talk about the circuit-based, obviously there are ways. We have worked on it. Actually, we patented a technology called concealing gate, which obfuscates the emission of transistors that are holding the key or passing the key from the memory to the logic. Okay, so you are introducing overhead in terms of the area, a little bit on the power, depending on how far your logics are from where your key is saved, and so on. But I would say we also introduced another technique, nano pyramids, where by applying these pyramids which are used in the solar cells, one can obfuscate the reflected laser coming from these machines. A very good technique that can be used. But as we go to 7 nanometer, as we go to smaller nodes, your attack approaches are going to be different. And I don't have a slide on it, unfortunately, here. But the same approach that can be done with optical can be done with electron probing as well. It's not going to be contactless. Obviously, you have to do more sample preparation. But because we are talking about FinFETs then, an advanced sample prep approach, you can basically prepare your chip down to the fins, but still your chip is active. So the passive voltage contrast will help to basically collect images and read them the way they are charged or discharged. But work on progress. Yeah, that's actually a very niche area we are working on right now.
Very good, thank you. If you'd like to continue your presentation.
Right. All right, sure. Thanks, Reward. So the rest of the talk will be about the PCBs. A few slides on the printed circuit boards. Big topic, again, BCAC, other routers that have been not easily, but with some social engineering and addition and tampering of the components and understanding of the circuit, one can tamper with them, one can bypass some of the securities, and has been more and more attention to this problem over the past couple of years. Back in 2015, we published a paper on how with an X-ray imaging, one can extract all the traces of a PCB. So 5, 6, 7 layers PCBs, which really doesn't matter the number of layers when we talk about regular tomography. These X-ray imaging techniques and sources, again, are coming from the medical domain, the same way a CT scan machine works. The X-ray machines are working as well. Of course, the power is different. The way the sample is mounted and the spin is different. But the noise is very much different. We don't get a lot of noise in medical applications because X-ray inherently is getting a lot attenuated when we have high Z material. So all the soldering material, all the capacitors with lead in them, the ports with all those leads, they are going to attenuate the X-ray, and that is going to cause noise when the 3D image is being reconstructed. So this work that we did back then was on an unpopulated board. So as soon as the board is getting populated, the challenge come in. And it is not just about the connections of the board. That's half of it. The rest of it is going to be the components. It's going to be what components are there, what is written on the board. We have reference designators. We have the components markings, logo, and a lot more information that have to be extracted, compiled, and make sure that they are the right one that are supposed to be there. So wide variety of modalities can actually help here. Optical inspection is one way. A good number of works out there with respect to some of the companies like CyberOptics and Cognex. They have different machine learning based algorithms that after collecting the images, they would be able to extract the package type and marking of it. But as soon as you look into the whole board, you get a ton of false positives. And to get rid of those false positives, to make sure that we have a fully automated process, that you put a PCB in, you collect images with an optical mode or an X-ray and a thermal. What is that best combination of different modalities that you should implement to assure the structure of your PCB, the components that are on it, the markings, the logo that are on it are the right one? Okay, so includes, again, image processing, machine learning. We have a good number of probably 30-40% of my students in the team are working on machine learning and AI algorithms. What is the best? And these AI algorithms are not necessarily have to be built from the scratch. There are a good number of them from the natural images, but nowhere close to what they should be for electronic applications. So I also talked about the different modalities. So on the top of these modalities that we are working on are the regular cameras or optical microscopes. It's much more easier for an end user to just use his cell phone and collect an image, send that image to a cloud or some trusted entity. Those images get analyzed, all the bill of materials get extracted, and the user gets notified whether or not that's the right board, whether or not there is no case like the big hack. Obviously, optical is only focusing on the surface features, right? What if there is a component which has a marking defect on it? It's a chip which is aged, which is old, but the marking is polished away and a new marking is printed. So then other modalities comes in. X-ray, terahertz is, I think terahertz hasn't got enough attention that it should. It's a new modality and rich, a lot of data which can be extracted. We are adding one to our lab very soon, and information from the package structure, from the polymer, the encapsulant can be extracted as a fingerprint or also as an image. So same with the PCBs, we need data. We need data, which unfortunately we don't have enough. And then again, we started to have our own database. So right now we are collecting the images, optical, and soon X-ray as well to put in this database. So far we have about 100,000 of images. Once you have the images, you need to get them annotated to let your algorithms and neural networks know what are those images. And that's a very difficult part of the job. So in our team, we have groups or army of students, 10, 20, 30 undergrad and master students who are helping us to do the annotation, learn the algorithms, depending on what sort of those algorithms can understand from the images, what are the features that has to be annotated. Okay, so, and a lot of different components, ICs, these are 4 or 5 examples of common components that we see on the PCBs. In addition, we have sensors, we have transducers, we have transistors, and so on and so forth. So to conclude this area of physical inspection, I think we have just scratched the surface. We talked about, this is probing attacks, different type of probings. We talked about the optical probing on the ICs. Optical probing is actually getting attention because the packaging is moving more and more toward the Philip packaging. And when we have these Philip packages, the backside silicon is transparent to the emission of the IR and near IR. So the wavelengths of 1.1, 1.3, these lasers can actually pass through, the emission of the transistors can pass through, and the image can be collected. Thermal probing, E-beam probing, electron probing, I just briefly touched upon it. It is next 2-3 years, I think it's going to be getting a lot more attention, same as the optical that it is doing now. Of course, requires much more advanced sample prep, but sample prep is catching up very fast. On the contact-based, the probing, the arm-based probing, or on the other side, we have all these scanning probe microscopes. We have microwave modality. We have the capacitance microscopy, and also recently the quantum microscopy and SSRM and SNDM and so on. These things haven't been explored enough from the perspective of the assurance. That image on the top right is an image of a SMIM scanning microwave impedance, which can be used to read the tamper-proof memory flash. When we have the charge and not charged data, they come out as bright and darker features. So we require sample prep. Obviously, this is not non-destructive, but goes down only to about 100 nanometer or 200, about hundreds of nanometers. So the whole chip is still active. So what should we do to prevent these? First, we have to fully understand them, but what we should do to prevent after we understand what the principle of it works. So I know we probably don't have a lot of time as well. I'm done with my slides. We were lucky to publish the first book on physical assurance. And at University of Florida, we also have a course I teach on the physical assurance where students can get hands-on, hopefully after COVID, experiment on these machines, do some projects, undergrad students, master and PhD. We started our YouTube channel as well, starting to talk about the packaging and physical assurance, where our students help. And also, finally, the PAINE conference. If you are interested more in the physical assurance topics, we have this conference 2021 is going to be the fourth conference, which is an IEEE, and November 30th, we will have it this year. And with that, I'm done with the slides and happy to take any questions if there's any.
Well, Navid, thank you for a fascinating presentation. I would remind the attendees that there is a Q&A bubble at the bottom of your screen. If you press on that and type in your question, I will pose that to Navid. While the questions are being keyed up, I did have a question. You talked about terahertz imaging as an emerging opportunity. Can you tell us a little more about that?
Of course, yeah, sure. So terahertz is one of the modalities which has been more used in basically coding applications. It has very high resolution in identifying the quality of the paint coding, especially in automotive industry. Then it went into the pharmaceutical, looking into the pills, the material and characterization in the pills, and now more and more in the electronics. So there are a couple of companies working on it right now. Because the terahertz has this high frequency and the data that can be extracted are rich, a lot of information from the terahertz, there is a good chance that now we're working on it, we can come up with these unique fingerprints. So if you have a package that encapsulates, so we, I had a few slides, maybe glad you asked that question. Oh, unfortunately, I don't have it here. But in the package, we have a lot of different components, right? We have fillers, we have accelerators, we have the recipes that are used, what temperature or how the molding has happened. So each of them eventually will have an impact on the package. So the question now is, can we use these other modalities or a combination of them combined with machine learning to come up with a unique fingerprint for such packages? So if there is something different on the package encapsulant, then this fingerprint will be also different, and we will be also able to extract that. So this is something which the perspective we are getting into this is to look into stuff that are not requiring anyone to enforce a logo or a tag or anything on top of what the physical structure of the chip is. So just its physical structure and integrity of the component themselves. So on PCB level, there are also some work. X-ray is doing much better on the PCB level compared with the terahertz. But on IC level, I think there are really some promising techniques and opportunities that terahertz can help the assurance community.
Yep. Thank you. We do have one question. Are you doing work on counterfeit whole circuit boards, laminates, solder masks, solder for assembly? The symptom here, I guess, is assembled boards which burst into flames when they should not. And I guess you would be able to detect if the appropriate materials were used or if some counterfeit materials were used.
So that's a very good question. Very good question, and part of the problem, right? I mean, right now we are starting, even everything out there is right now try to just authenticate the board itself. So when we talk about the defects, that's what I guess this question is about. So on the defect side, definitely there is a ton there. We are working on it, yes. Getting to the questions, yes, we are working on it, trying to extract those features. Like, what is that feature that under an X-ray or a terahertz or an acoustic or even an optical, you can understand that would raise a flag for you that there might be some defects or a sign of a counterfeit on this chip. Even under optical, the reflection of some of the soldering material may be different. The texture may be different. If the resolution of the optical is high enough, there are correlations between the texture or the reflection with the potential defects into these. And same with the solder mask, and so on. So this whole thing is basically goes back to the analysis of the data. To find out those clustered relations between the defects and the signatures or the signs, we need to do those studies. From the simulation, there is a lot we can do, obviously, but there are always these unknown unknowns. Once we have this platform or the structure to collect all these data and look into them completely and analyze them, we will be slowly able to build up and cover the whole thing. When we talk about the X-ray by itself is just a huge thing. We are working on building our own X-ray machine. Everything out there is great. A lot of companies are working on X-ray imaging, but again, the principle of them, their reconstruction algorithms, their segmentations are based on medical applications. So with the electronics, especially PCBs, we should collect images in a different trajectory, not just circular tomography. They have to be different. Recently, I guess one of the companies introduced the helical imaging for acquisition of the X-ray images, which is very good and is a good step forward. But we are also working on our own X-ray machine. New X-ray sources are coming out with much better sharpness and phase contrast. When we look into these attenuation on the solder material, those high contrast X-ray sources are going to help a lot.
Good. Thank you. Well, no more questions at this time. We do have an attendee, Sajjad Bahradar, says, thank you very much for a great presentation. And I'd certainly like to give my thanks for a very detailed look at how we can get into the products and validate the various components. So thank you for that.
Yeah. Thank all our speakers today for the excellent presentations and tackling all the questions they got. So thank you very, very much. I also like to take a moment to thank our sponsors once again, Amcor Technology and Advantest. Amcor, as a leading OSAT, has multiple differentiators in the area of technology, quality, and service technology in the areas of the advanced packaging leadership, engineering services, and their broad portfolio. Quality through a quality first culture, execution and automation, and service through design and test through dropship, manufacturing footprint, and local sales and support. So Amcor, we thank you. And Advantest, we'd also like to thank, who was recently rated by VLSI Research as the best ATE company in 2020. Very high ratings in, with a score 9.5 out of 10 in the various categories: technical leadership, partnership, uptime, commitment, trust and supplier, quality results, product performance, and recommended supplier. So congratulations to Advantest, and thank you again for sponsoring. And lastly, I'd like to thank everybody for attending. We will have the slides and videos up next week. You will receive an email, but I want to thank everybody for joining us today and look forward to seeing you at a future MEPTEC event. Thank you.